Right now, in the room where you are lying, something is passing through you. It has been passing through you for your entire life, and it will keep passing through you after you fall asleep tonight, and it will not slow down, and it will not stop, and you will never feel it, not once, not even slightly. Billions of these particles cross your body every second. Almost none of them touch anything. In an average year, if the physics is what most researchers currently believe it to be, something on the order of 10 of them will actually strike the nucleus of one of your own atoms. 10 collisions, spread across 365 days, inside a body made of tens of trillions of cells, each built from atoms whose nuclei are on the scale that matters here, almost entirely empty space. That is how rarely it touches anything. And here is the second half of it. This same invisible traffic accounts for roughly 85% of all the matter in the universe. Everything you can see, weigh, and touch, every star, every planet, every atom in your own hand is the remaining 15. We have measured this. We have mapped where it sits, in galaxies and between them. We do not know what it is. Tonight is about that specific gap, the distance between knowing precisely how much of something exists and having no idea what it is made of. If you find this kind of slow, specific exploration useful for sleep or for winding down, a like or a subscribe genuinely helps this channel keep going. And if you would like, drop your location and the time where you are listening from in the comments. I am always a little curious how far this reaches. Here is the question worth sitting with for the next few hours. How does a civilization build a confident, precise map of something it has never once detected directly? By the end of tonight, you will know exactly how we arrived at that number, 85%, and exactly why, after more than a century of looking, nobody can tell you what is on the other side of it. Start with the number itself, because it is far more exact than it has any right to be. The most careful measurements available place the contents of the universe at roughly 5% ordinary matter, the atoms that make up you, the room, the planet, the stars 26% of something we call dark matter, and the remainder, close to 69%, in a separate mystery called dark energy, which is a different story for a different night. 5 and 26. Not mostly this, or roughly that. 5 point something, 26 point something. The kind of precision you would expect from counting coins, applied to something nobody has ever held. Those two numbers, 5 and 26, are where the 85% comes from. Set the dark energy aside. It is not matter. It is something stranger, a property of space itself. Look only at the matter. 26 parts of one kind, 5 parts of the other. Divide the first by the total and you get 85%. That is the whole arithmetic. There is nothing hidden in it. The strangeness is not in the calculation. The strangeness is that we can do the calculation at all. The physicist Catherine Fries has spent much of her career on exactly this problem, and she has written about the evidence in unusually flat, unhedged language. Measurements of the ancient light left over from the early universe, she has said, provide irrefutable evidence for the existence of dark matter. Not a hint, not a suggestion. Irrefutable, and yet the thing being confirmed remains, after all these decades, a placeholder. A name for a gap in the ledger, not a description of what fills it. Here is a way to hold the imbalance. A human body is dense. Roughly 1,000 kilograms packed into every cubic meter, about the density of water, which is why you can stand on solid ground and feel solid yourself. Now, take that same cubic meter and empty it, no air, no dust, nothing, and fill it instead with dark matter at the density researchers believe exists out here, in this part of the galaxy. The number you get is smaller than the density of your own body by a factor with 24 zeros after it. At that point, the comparison stops working as arithmetic and becomes something simpler. Almost none of it is here. Not in this room, not in this solar system, not in any particular place you could point to. And yet all of it, the whole 85%, has to be somewhere. It has to add up. The places where it genuinely concentrates are the vast, dim halos wrapped around entire galaxies, structures that extend far past the last visible star and hold enough mass to explain why those galaxies do not fly apart. Here, in the thin outskirts of one ordinary solar system, tucked inside the bright disk of one ordinary spiral galaxy, we are living in an anomaly. We are inside a rare, dense knot of ordinary atoms. Locally, on the scale of a room or a planet or a solar system, ordinary matter wins. It is only when you back away far enough to see whole galaxies that the proportion flips and the atoms become the rounding error. The detectors built to catch this material rest on a specific set of assumptions about how it moves. The working model has it drifting past the solar system at something like 220 kilometers per second, not because it is aimed at us, but because the sun is ploughing through a halo that does not rotate with the disk. The fastest of it, the particles least bound to the galaxy, could reach roughly 540 kilometers per second before escaping the pull of the Milky Way entirely. Multiply that speed by the assumed density. Physicists commonly use a figure of about 0.3 of a billion electron volts of mass in every cubic centimeter of space out here, and you get a flow rate. How many of these particles should cross a given patch of matter in a given second? That flow rate is where the 10 collisions a year figure comes from. It is not a guess pulled out of the air. It is an equation with 3 inputs: an assumed mass for the particle, an assumed speed, an assumed mass, and the ordinary physics of how two objects collide when one of them is mostly empty space. The only real unknown left in it is the identity of the thing doing the colliding. Change that one unknown and the answer moves enormously. Physicists working the same arithmetic for lighter candidate particles in a mass range that once seemed to match some contested early experimental hints found the rate could climb as high as 100,000 collisions a year. That is roughly 1 every 5 minutes, every hour, of every day you have been alive. Still nothing you would ever feel. Still no injury, no signal, no trace left behind. The natural radiation you absorb from the ground beneath the building, from the stars overhead, from the potassium in a banana, outweighs it by an enormous margin, but the fact stands. Somewhere between 10 times a year and once every few minutes, the material that makes up most of the mass in the universe is reaching into you, personally, and touching something. Add it all together, every human body alive on Earth right now, all 8 billion of them, and every trace of dark matter inside every one of them at this exact instant, and the total comes to less than 1 nanogram, a speck lighter than a grain of pollen. That is the entire human share of the invisible 85%, a quantity too small to register on any scale ever built, held inside a species that has nonetheless managed to weigh the whole of it, precisely, using nothing but the way distant things move. It is worth saying that dark is a poor name for it, and everyone who uses the term knows this. Dark suggests black, something that absorbs light, the way soot or a shadow does. This material does not absorb light. It does not emit light, reflect light, scatter light, or block light. A beam of starlight travelling through a dense halo of it arrives on the other side unchanged. It is not dark. It is transparent in a more complete way than glass is transparent, because glass at least bends what passes through it. This does not even do that. The only thing it does is pull. Some researchers have argued the field should have called it invisible matter or transparent matter, and that the choice of word has quietly shaped how the public imagines it as something looming and shadowed, rather than as something that simply is not in the way. Here is the shape of the thing, as far as anyone can reconstruct it. Picture the Milky Way as you have seen it in photographs. A flat, bright spiral, 100,000 light-years across, with a thickened bulge at the centre and arms winding out through it. That is the part that shines. Now picture that entire structure sitting at the middle of a rough sphere, extending perhaps 5 or 6 times further out in every direction, containing several times more mass than everything visible put together. The bright spiral is not the galaxy. The bright spiral is a small, dense, luminous deposit near the centre of the galaxy, which is mostly a halo, and the halo is mostly nothing you can see. Every star you have ever looked at with your own eyes lives inside that deposit. All of them. The furthest stars visible to the unaided eye from a dark site are a few thousand light-years away, which does not get you out of the local neighbourhood, let alone to the edge of the disk, let alone into the halo. The entire visible sky, everything the human species observed for its first 300,000 years, is a small, bright interior region of an object we cannot see the outside of. There is one more detail about the local flow that matters, because it produced the only claimed detection in this whole field. The Earth does not move through the halo at a constant speed. The solar system carries us through it in one direction, and the Earth's orbit around the Sun adds or subtracts from that motion depending on the time of year. Around the beginning of June, the two motions add, and we move through the halo faster. Around the beginning of December, they partly cancel, and we move through it more slowly, which means a detector on Earth should register slightly more collisions in June than in December. Not a huge difference, a few percent, but a very specific, very predictable, annually repeating signature that no ordinary source of background noise would produce. An Italian experiment called Dharma, running under a mountain in central Italy for more than 2 decades, has reported exactly that modulation, at high statistical significance year after year. It is the one long-standing positive claim in the field. It is also, as of now, not accepted, because every other experiment that has searched the same parameter range with different target materials has found nothing, and several purpose-built replications using the same material have failed to reproduce it. The most likely explanation involves some seasonal effect in the detector or its surroundings that nobody has fully identified. But it has not been definitively explained away either, and it has been sitting there, unresolved, for a very long time. You can lie there and try to feel it. There is nothing to feel. There is no pressure, no warmth, no faint wind. The particles do not push on you, because pushing requires an interaction, and interaction is the one thing they almost never do. They pass through the wall, through the mattress, through your ribs and your lungs, and the blood moving in them, through the floor and the foundation, and the rock beneath the foundation, and out the far side of the planet, and away. The Earth is not an obstacle. To this material, the Earth is essentially transparent. 8,000 miles of iron and stone, and most of them will not notice it was there. That is the real puzzle worth sitting with tonight, and it is not yet a puzzle about dark matter. It is a puzzle about method. Nobody has ever seen this material. Nobody has held a sample, isolated it in a jar, watched it glow or spark or do anything at all. And yet we have a percentage, 26, precise to a decimal place. The question this whole night exists to answer is how anyone arrives at a number like that, about something that has never once been observed directly, and why that same method, pushed as hard as it will go, still cannot tell us what the substance is. The answer begins with a piece of physics old enough to be unglamorous. It is called the virial theorem, and it rests on an idea so basic it feels almost like cheating. Things held together by gravity move at speeds that depend on how much mass is doing the holding. Swing a rock on the end of a string. The harder the string pulls, the faster the rock can travel without flying off. Let go, and it leaves in a straight line. Gravity works the same way, with no string. If you know how fast something is orbiting, and you know how far out it is orbiting, you can calculate exactly how much mass must be sitting at the center to keep it from leaving. The calculation does not require seeing the mass, and it only requires watching the motion. That is the whole trick, and every piece of evidence in this story is a variation on it. Here is where the tidy picture first cracked. Astronomers pointed their instruments at spinning galaxies and expected something very specific. Stars, near the bright center of a galaxy, should orbit quickly. Stars far out near the faint edges, where most of the visible starlight is behind them, should orbit slowly the same way Mercury circles the Sun far faster than Neptune does, simply because Mercury sits deep inside the Sun's strongest pull, while Neptune sits out where that pull has thinned. This is not a hunch. This is Newton, tested and confirmed inside our own solar system for 3 centuries. Astronomers expected the same falling off curve in galaxies at every scale everywhere they looked. What they measured instead was flat. Stars out near a galaxy's faint outer edge were moving just as fast as stars deep inside its bright center. Sometimes faster. By the visible mass alone, those outer stars should have been thrown off entirely, scattered into intergalactic space within a single rotation of the galaxy. They were not. Something with real mass and no visible light had to be sitting out there, extending the gravitational reach of the galaxy far past the point where the galaxy appeared, to the eye, to stop. A completely separate method, arrived at the same conclusion from a different direction, and it does not involve orbits at all. It is called gravitational lensing. General relativity predicts that mass bends light, not as a figure of speech, but measurably, the way a glass lens bends it. A massive cluster of galaxies sitting between Earth and something further away will warp the light from that distant object as it passes, smearing it, stretching it, sometimes splitting it into multiple images. Measure the amount of that distortion carefully enough, and you can calculate how much mass the cluster contains. Not the mass that glows, the total mass. Do this across enough clusters, and a second number falls out, arrived at without a single assumption about rotation speed or orbital velocity. It keeps landing in the same place the rotation curves do, far more mass than the visible galaxies can account for. Then there is a third method, and it is the strangest of the three, because the light it studies is older than any star. Roughly 380,000 years after the beginning of everything, the universe cooled enough for something specific to happen. Before that moment, the cosmos was a hot fog of loose protons and electrons, and light could not travel through it. Every photon scattered off a charged particle almost immediately, the way a car's headlights scatter in thick fog. Then the temperature dropped far enough for protons and electrons to combine into neutral hydrogen. The fog cleared, all at once, everywhere, and the light that had been trapped inside it was suddenly free to travel in a straight line. It has been travelling ever since. It reaches Earth today as a faint microwave glow, arriving from every direction at almost exactly the same temperature, a little under 3 degrees above absolute zero, and it is not perfectly smooth. Baked into it is a pattern of temperature ripples, differences of about 1 part in 100,000, imprinted at that exact moment and unchanged since. 3 space missions have mapped that pattern with increasing sharpness. The Cosmic Background Explorer launched in 1989 and made the first detection of those ripples in 1992. The Wilkinson Microwave Anisotropy Probe launched in 2001 and released its first full-sky maps in 2003. The Planck satellite launched in 2009 and finished collecting data in 2013. Each one saw the same sky more finely than the last. What is encoded in those ripples is a sound recording. Before the fog cleared, the ordinary matter in the universe was locked to the light, and the two behaved as a single fluid. Gravity pulled that fluid inward toward denser regions. The pressure of the trapped light pushed it back out. In and out, over and over, genuine acoustic waves, moving through the plasma of the early universe at a large fraction of the speed of light. When the fog cleared, those waves froze where they stood, and their pattern is still visible in the temperature of the sky. Dark matter does not participate in that oscillation. This is the important part. Whatever it is, it does not feel the pressure of light." End quote. So while ordinary matter was bouncing in and out, dark matter simply sat in the gravitational wells and kept accumulating, deepening them, without ever being pushed back out. The two behaved differently, and because they behaved differently, they left different marks. Read the ripples carefully, and the height of one particular peak in the pattern tells you how much ordinary matter there was about 5% of everything. The heights of the peaks around it tell you, independently, how much of the other kind there had to be. 26%, present at the very beginning, shaping how matter gathered before a single star existed. If you remove the dark matter from the model, the pattern in the sky would look measurably different. It does not look different. It looks like the version with the dark matter in it. There is a fourth constraint worth naming, because it closes a door that would otherwise stay open. In the first few minutes after the beginning, the universe was hot enough to fuse hydrogen into helium and traces of lithium and deuterium. How much of each got made depends very sensitively on how many ordinary protons and neutrons were available at the time. Measure the abundance of deuterium in ancient, unpolluted gas clouds today, and you can work backward to the density of ordinary matter in those first minutes. The answer agrees with the 5% from the ripples, which means the missing mass cannot simply be ordinary matter we have failed to spot. If it were made of protons and neutrons, the early universe would have cooked a different mixture of light elements than the one we actually find. So, spinning galaxies, bent starlight, the oldest light in the sky, and the chemistry of the first 3 minutes. None of them looking at the same objects. None of them built on the same assumptions. None of them capable of contaminating each other's results. All of them arriving at the same figure, within a few percentage points. That convergence, not any single measurement, but the agreement of unrelated approaches is what moves this from a suspicion to settled physics, while leaving the identity of the thing being measured completely open. It was not always this settled, and the way it settled is worth a moment. In the years before the sharpest satellite measurements arrived, one of the leading models proposed a mixture, roughly 60% of the dark matter in a cold, slow-moving form, 30% in a hot, fast-moving form made of a lightweight particle called the tau neutrino, the remaining 10% as ordinary atoms. For a while, this blend fit the available data reasonably well. It was a serious proposal, worked through by serious physicists. And it was wrong. It did not fail dramatically. Nothing collapsed. What happened was slower and more ordinary. Measurements got sharper, and the sharper they got, the less the mixed recipe matched, and the more a much simpler one did. Dark matter that is overwhelmingly cold, moving slowly compared to the speed of light, with no significant hot component required at all. The reason the distinction matters is structural. Fast-moving matter smooths things out, it streams away from small clumps before they can collapse. Slow-moving matter lets small structures form first and merge upward into larger ones. The universe we can see, with its small galaxies assembling into groups and groups into clusters, is the one the cold recipe predicts. There is a fifth line of evidence, and it is the one that convinces theorists more than any of the others, because it is not a measurement of mass at all. It is a question of timing. Run the universe forward in a computer. Start with the tiny density variations visible in the oldest light, 1 part in 100,000, no more, and let gravity work on them for 13.8 billion years. Ordinary matter alone cannot do it. The reason is the same reason the acoustic peaks exist. For the first several 100,000 years, ordinary matter was locked to the light, and the pressure of that light kept smoothing out any clump that tried to form. Structure could not begin growing until the fog cleared. Start the clock then, with only ordinary matter, and there is not enough time. You end up with a universe far smoother than the one we live in. No mature galaxies at high redshift, no rich clusters, nothing like the great filaments and voids that galaxy surveys actually map. Add dark matter and the timing works. Because it never felt the radiation pressure, it was free to start clumping much earlier, while ordinary matter was still trapped in the fluid. By the time the fog cleared, there was already a scaffolding of gravitational wells waiting. Ordinary matter fell into structures that had been quietly assembling for hundreds of thousands of years, and galaxy formation started with a substantial head start. That is why simulations of cosmic structure look like the real sky, and why simulations without dark matter do not. It is not a subtle statistical preference. It is the difference between a universe with galaxies in it and a universe without them on the schedule we observe. There is a sixth, and it is a ruler. Those same sound waves in the early plasma left a preferred distance scale, a characteristic separation, frozen in when the fog cleared, of about 500 million light-years in today's units. That scale should still be faintly visible in the way galaxies are distributed, as a very slight excess of galaxy pairs at that particular separation. It is far too subtle to notice by eye, but with enough galaxies it emerges from the statistics. Surveys mapping millions of galaxies have found it. Its size, measured at different distances and therefore at different times in cosmic history, provides an independent handle on the composition of the universe. It agrees. That is a small footnote worth keeping in mind for the rest of tonight. The confident 26% was not the first answer anyone tried. It is the one that survived the next round of instruments, which raises an obvious and slightly uncomfortable question about the current answer, and there is no honest way to close that question tonight. None of this, though, tells you who first noticed that something was missing. Every method just described reached its current precision using satellites, radio dishes, and digital detectors that did not exist for most of the 20th century. But the discrepancy itself, the raw fact that galaxies and clusters were somehow holding together with far more mass than anyone could see, was noticed long before any of that. It was noticed repeatedly by different people in different countries working on different problems. Some of them wrote it down clearly. At least one of them looked directly at the answer, described it accurately, and explained it away. The Dutch astronomer Jacobus Kapteyn spent the early part of the 20th century trying to map the Milky Way from the inside, which is roughly like trying to draw a forest while standing among the trees. He counted stars, measured their motions, and built a model of the galaxy's shape from the statistics. In 1922, working through the numbers on how stars move up and down through the plane of the galactic disk, he used a phrase that had not been used that way before. He wrote about dark matter meaning precisely matter whose existence is suggested by its gravity and by nothing else. He was not announcing a discovery. He was naming a category, and then reporting that the category appeared to be nearly empty. His calculation suggested there was very little invisible material in the Sun's neighbourhood. An Estonian astronomer, Ernst Opik, had run a similar analysis 7 years earlier and reached the same conclusion. The known stars and gas were enough to explain the motions, nothing extra required. 10 years later, another Dutch astronomer took the same measurement and got a different answer. Jan Oort was one of the great galactic astronomers of the century. He worked out the rotation of the Milky Way, gave his name to the vast reservoir of comets at the edge of the solar system, and had a long, careful, unshowy career of getting things right. In 1932, he published a study of exactly the problem Kapteyn had worked on, how stars oscillate vertically through the galactic disk, rising above the plane, falling back through it, rising again. The frequency of that oscillation depends on the mass of the disk pulling them back down. Count the stars, add up their light, convert to mass, and compare. His numbers did not close. The disk appeared to contain more mass than its visible stars could account for. The gap was not enormous, a factor of perhaps 2, but it was there, and he reported it plainly. He had found what would later be called the local missing mass problem, and it is worth saying that this particular problem has since largely dissolved. Better star counts, better accounting for faint stars and cold gas, and much better data from later surveys narrowed the gap until most of it disappeared. The disk, as far as anyone can now tell, is mostly made of things we can see. The halo is where the real discrepancy lives, and he was not measuring the halo, so the first careful measurement pointing at missing mass turned out to be pointing at the wrong place. That happens. It is not a failure of the method. The method was sound and is still in use. It is what the data looked like from inside the galaxy in 1932. The following year, in a Swiss physics journal, in German, a paper appeared about a cluster of galaxies. It is the paper this story usually starts with, and it will get its own section shortly. Set it aside for a moment, because the next episode is stranger and less well known, and it happened in California. In 1939, a young astronomer named Horace Babcock published a rotation curve for the Andromeda galaxy, the nearest large spiral to our own, the smudge of light you can see with the naked eye on a dark night, if you know where to look. He had obtained his spectra using the 36-inch refractor at Lick Observatory in Northern California, a telescope by then already half a century old. Andromeda is faint and enormous, and its outer regions are very dim. Getting velocity measurements from the far edge of it, in 1939, with photographic plates and a 19th century refractor, was slow and difficult work. What Babcock found was that the outer parts of Andromeda were rotating far faster than they should have been. Not slightly faster, far above what the visible mass predicted. The curve did not fall off toward the edge the way Newton required, it rose. This is, in substance, the result that would make Vera Rubin famous 31 years later. Babcock did not conclude that Andromeda was surrounded by invisible mass. He offered 2 other explanations, both of them reasonable at the time. One was that the ratio of mass to light might simply change as you move outward, that the outer regions might be full of dim, low mass to light ratio material of an ordinary kind. The other was dust. If the light from the outer galaxy were being absorbed and reddened on its way to us, the measurements might be distorted in ways that produced a spurious curve. Interstellar dust was a live and genuinely confusing problem in the 1930s. It had recently made a mess of galactic distance estimates. Suspecting dust was not foolish. It was the responsible thing to suspect. He was looking directly at the evidence. He described it accurately. And he interpreted it away, because the alternative, an enormous quantity of matter that emits no light at all, wrapped invisibly around a galaxy, was not a hypothesis anybody had a reason to prefer yet. Babcock went on to a substantial career. He became director of the Mount Wilson and Palomar observatories. invented instruments that are still conceptually in use, and did foundational work on the magnetic fields of the Sun and of stars. His father was an astronomer too, at the same observatory. Between them, the Babcocks put in something close to a century of observing. The rotation curve of Andromeda is a footnote in his own bibliography. The next year, in 1940, Oort came back to the problem from the other end. He studied an edge-on, lens-shaped galaxy measuring how fast it rotated and how its brightness fell off with distance from the center, and found that in its outer regions, the ratio of mass to light reached something like 250. To put that in context, for the Sun, that ratio is 1, by definition. Because the Sun is the unit, a ratio of 250 means that for every unit of light coming out of that region, there are 250 units of mass sitting in it. No stellar population known then or now produces light that inefficiently. Oort noted the difficulty and moved on. Around the same time, other pieces were accumulating in other places, and nobody was assembling them. In 1937, a Swedish astronomer, Erik Holmberg, estimated galaxy masses from the way pairs of galaxies orbit one another and got numbers larger than the light suggested. Through the 1940s, multiple observers confirmed that galaxies in clusters were moving much too fast for the visible mass to hold them. The specific claim from that 1933 Swiss paper, checked and rechecked and quietly confirmed, without the conclusion being widely accepted. In 1957, a Dutch radio astronomer named Hendrik van der Hulst used a completely different technique on Andromeda. Neutral hydrogen gas emits radio waves at a very specific wavelength, 21 centimeters, and radio telescopes can detect that emission out well past where the starlight fades to nothing. It was, in effect, a way to see the outer parts of a galaxy that are invisible to an optical telescope. The hydrogen out there was rotating fast too. Same answer, different instrument, different part of the spectrum. In 1959, two astronomers, Frans Kahn and Lodewijk Volter, tried something cleverer still. The Milky Way and Andromeda are approaching each other. If you assume they started out moving apart with the general expansion of the universe, and that gravity has since reversed their relative motion, then their current approach speed tells you how much mass must exist in the local group to have accomplished that reversal in the available time. The number they got was roughly 10 times more mass than all the visible material in both galaxies combined. By 1960 then, the situation was this. There was evidence from the vertical motions of nearby stars, evidence from the rotation of Andromeda, taken optically, evidence from the rotation of Andromeda, taken by radio, evidence from the mass-to-light ratios of edge-on spirals, evidence from pairs of galaxies, evidence from the velocities of galaxies inside clusters, confirmed by many observers, evidence from the mutual approach of the two largest galaxies in our own neighbourhood, 7 independent lines spread across nearly 4 decades and half a dozen countries, all pointing the same direction, and there was no accepted theory of dark matter, because nobody had put the 7 lines on the same page. Part of this is simply how science looks from the inside when the pieces are scattered. Each result had its own local explanation available: dust, or bad distances, or an unusual population of faint stars, or a measurement that needed redoing. Any single anomaly can be absorbed. It takes a certain accumulated weight before absorbing them all starts to feel like more work than accepting the obvious. The change came in the 1970s, and it came in 2 stages. The first was theoretical. In 1973, Jeremiah Ostraker and James Peebles at Princeton ran calculations on the stability of galactic disks and found something inconvenient. A flat, spinning disk of stars, with nothing else around it, should not stay flat and spinning. It should buckle. It should grow a bar through the middle and distort. Most spiral galaxies visibly do not do this. What would keep a disk stable, their calculations showed, was a roughly spherical halo of mass surrounding it, containing a good deal more mass than the disk itself. That was a theoretical argument for invisible halos arrived at without reference to any rotation curve at all. And then, in 1974, 2 groups published independently, one in Princeton and one in Tartu, in Estonia Ostraker with Peebles and Amos Yahil, and Jan I. Nasto with Ants Karsik and Ensar. Both papers did roughly the same thing, gathered the scattered evidence, put it on one page, and stated the conclusion. Galaxies are surrounded by massive halos of unseen matter. The evidence, taken together, is difficult to escape. Two teams, on opposite sides of the Iron Curtain, reaching the same conclusion in the same year, from largely the same published literature that had been sitting there for decades. There is a pattern in all of this worth naming, because it recurs in the rest of tonight's story. None of these people were incompetent. Every one of the explanations they reached for instead of invisible mass was, at the time, more probable than invisible mass. Dust really does redden and dim starlight, and had recently caused serious errors in distance measurement. Distance scales really were unreliable, and would be revised repeatedly for another 40 years. Faint stars really do exist in large numbers and really do carry mass without much light. Every local explanation was defensible on its own terms. What made the difference was not one person being cleverer. It was the accumulation reaching a point where the number of separate defensible explanations required became larger than the number of things being explained. At that point, the simpler account that there is a great deal of matter out there that does not shine stopped being extravagant and started being economical. That transition took roughly 50 years, and nobody experienced it as a moment. The second stage was observational, and it belongs to a specific instrument and two specific people, working through the 1970s on galaxy after galaxy until the pattern became too consistent to argue with. That story is coming, but before it, there is the man who said it first, said it loudest, was right, and spent 40 years being ignored partly because his numbers were shaky, and partly because almost nobody in the field could stand him. In 1933, in Switzerland, a paper appeared in a Swiss physics journal under the title, translated, "Of the Redshift of Extragalactic Nebulae." It was written in German. Its author was a Bulgarian-born Swiss citizen who had been working in California for 8 years, and the section of it that matters here runs only a few pages. His name was Fritz Zwicky. He was 35 years old, employed at the California Institute of Technology, and he was studying the Coma cluster, a sprawling gathering of galaxies in the northern sky, one of the largest structures anyone had yet attempted to weigh. His method was the virial theorem, applied for what may have been the first time to something on that scale. He did it in two independent halves. The first half was to estimate the mass of the cluster from its light, add up the combined brightness of the galaxies, then convert brightness into mass using the simplest available assumption, that stars in these distant galaxies produce light in roughly the same proportion to their mass as our own sun does. That gives you one number, call it the photometric mass, inferred from light. The second half was to measure how fast the galaxies were moving relative to one another, not orbiting neatly, the way planets circle a sun, but churning, each galaxy carrying its own velocity relative to the cluster's average. Zwicky had 7 galaxies with measured velocities. 7. The Coma cluster is now known to contain something closer to 1,000. From the spread of those 7 velocities, using the virial arithmetic, he calculated how much total mass would be required to hold the whole thing together rather than let it disperse. Call this the dynamical mass inferred from motion. The two numbers did not match, not by a small margin, not by anything that could be waved off as measurement error. The dynamical mass came out enormously larger than the photometric mass in his original calculation, by a factor approaching 400. Modern remeasurements of the Coma cluster, using thousands of galaxies instead of 7, and vastly better distance calibrations, bring that ratio down substantially. But the imbalance itself survives. Redone today with every advantage he lacked, there is still far more mass holding the Coma cluster together than there is starlight to account for it. He gave the missing mass a name, in German, Dunkel Materie, dark matter. It is worth pausing on what he meant by that, because it is not what the phrase means now. He was not proposing an exotic particle outside the physics of atoms. He pictured something entirely mundane, cold, burnt-out stars too faint to register on a photographic plate, chunks of rock and metal too small to shine, thin, cold clouds of gas spread through the space between the galaxies. Ordinary material, in other words, just too dim for the equipment of the 1930s to catch. The idea that the answer might lie completely outside known physics had not occurred to him, or to anyone, because there was no reason yet to think it was necessary. In his picture, the missing mass was a technological problem. Build a better telescope and you would find it. 4 years later, in 1937, he wrote it all up again, this time in English, in the Astrophysical Journal, in a paper called On the Masses of Nebulae and of Clusters of Nebulae. It is a remarkable document. He laid out the virial method properly. He argued that galaxies themselves should act as gravitational lenses, bending the light of anything behind them, an idea that would not be observationally confirmed for 42 years, and which now, as we will see, is one of the primary tools used to weigh dark matter. He even suggested that measuring such a lens would give the mass of the lensing galaxy directly, without any assumption about its light. He was describing, in 1937, the technique that would eventually produce the most famous image in this entire field. Almost nobody built a career on any of it for the next 40 years. Part of the reason was the numbers. His distance estimate for the Coma cluster was wrong by nearly a factor of 10, and that was not really his fault. The conversion from redshift into distance depends on a quantity astronomers call the Hubble constant, and in the 1930s that quantity was badly off. It took decades of untangling to fix. There turned out to be two distinct types of the pulsating stars used as distance markers, with different intrinsic brightnesses, which had been silently mixed together. There were motions of galaxies that had nothing to do with cosmic expansion, contaminating the redshifts. There were calibration problems that were not resolved until the second half of the century. His basic finding held up. His specific numbers did not, and in a field where specific numbers are the currency, that was enough to keep the whole idea on the margins. He was also not alone in the finding, which should have helped. In 1936, an American astronomer named Sinclair Smith ran a comparable analysis on a different cluster, the Virgo cluster, with 30 galaxies instead of 7. He found the same thing, a dynamical mass considerably larger than the visible galaxies could explain. 2 clusters, 2 independent astronomers, the same discrepancy. Smith died young, at 39, a few years later. The result sat there, but there was a further reason the idea did not spread, and it has less to do with the data than with the man delivering it. By nearly every account from people who worked alongside him, Zwicky was difficult in a way that went well past ordinary academic friction. He described the contents of astronomical journals as useless trash. He said, reportedly more than once, that astronomers were spherical bastards, explaining the insult by noting that no matter which angle you viewed such a person from, the assessment held. 220. Colleagues who accepted the expanding universe he called horses' asses. At one point he was barred from using the 200-inch telescope on Palomar Mountain after a dispute with the observatory's administration, and he was still angry about it decades later, telling a younger colleague near the end of his life that they had invented a special rule for the sole purpose of keeping him off it. His relationship with the astronomer Walter Bade deteriorated to the point where stories circulated of outright threats. This is a particular loss, because the two of them had done extraordinary work together. In 1934, only a year after the Coma paper, Bade and Zwicky proposed that the collapse of a massive star's core could produce an object made almost entirely of neutrons, a neutron star, 33 years before the first one was detected. In the same work, they coined the term supernova and suggested that such explosions were the source of cosmic rays. 3 ideas, all essentially correct, in one collaboration. And when a rattlesnake turned up inside the dome of the 18-inch telescope he liked to use, he accused Bade of putting it there. None of that made him wrong. It made him easy to set aside. A brilliant and combative man, publicly contemptuous of the community whose attention his idea needed, proposing something with no mechanism attached, no supporting theory, and no urgent reason to be preferred over the much simpler assumption that astronomers had merely underestimated how much light a distant galaxy produces. His dark matter sat in that uncomfortable position for 4 decades. Not disproven, not confirmed, mostly unexamined, attached to a name that made people reluctant to spend their careers on it. He kept working. He catalogued more supernovae in his lifetime than anyone in history had up to that point, well over 100, in an era when a handful was considered a substantial career total. He compiled catalogues of galaxies and compact galaxies that were still in use long after his death. He pushed for the small, wide-field Schmidt telescopes that made survey astronomy possible. He wrote a book arguing for a method of scientific thinking he called morphological, which is largely unread now, and which was in part a long complaint about how the field failed to consider possibilities it found unfashionable. He died in February of 1974 in Pasadena. He was 74 years old. It is worth being precise about what his method assumed, because the assumptions are where the argument actually lives. The virial theorem applies to a system that is bound and settled, one that has had time to reach a rough equilibrium, with its members orbiting in a stable statistical arrangement rather than flying apart or still falling together. If the Coma cluster were not bound, if it was simply a chance alignment of galaxies moving independently through space, the calculation would mean nothing. He argued it was bound, on the grounds that such a rich concentration of galaxies is very unlikely to be an accident of perspective. He was right about that, and it took decades of further observation to prove it. The other assumption was the conversion from light to mass. He used the Sun as his reference, which was the only sensible choice available. If the galaxies in Coma were full of stars far dimmer per unit mass than the Sun, small, cool, red stars, of which the universe turns out to contain enormous numbers, then his photometric mass would be too low, and part of the discrepancy would evaporate. This was, for years, the standard objection, and it was a fair one. It just turned out not to be nearly large enough to close a gap of that size. There is a side of him that does not fit the caricature, and it deserves a sentence. During and after the Second World War, he worked on jet and rocket propulsion, and he was decorated by the United States government for it. He spent considerable personal effort organizing the shipment of books and scientific equipment to libraries and observatories in Europe that had been destroyed, and he set up a foundation for war orphans. The man who called his colleagues spherical bastards also spent years quietly rebuilding institutions he had no professional stake in. He also spent decades arguing, in print and at length, that astronomy as a discipline was failing to look for things it had no theoretical reason to expect. He gave this a name, the morphological method, and wrote a book about it that almost nobody reads. Stripped of the terminology, the argument was that researchers systematically overlook possibilities that do not fit the framework they already hold. He believed this had happened to neutron stars, to supernovae, to gravitational lensing, and to the missing mass in Coma. In each of those 4 cases, he was, eventually, shown to be correct. That was the same year the 2 review papers appeared, the Princeton group and the Estonian group, independently gathering the evidence and stating the conclusion he had reached 41 years earlier. Whether he saw either of them is not clear, and it was 3 years before the observation that would finally force the whole field to take the 1933 claim seriously. That observation did not come from another cluster of galaxies. It came from a single spiral galaxy, studied more closely than anyone had studied one before, by 2 people using an instrument built specifically for the purpose, and by a woman who had deliberately chosen the safest, least controversial problem she could find, precisely so that she would be left alone to work. Her name was Vera Rubin, and she had been fighting for a place in this field since long before she pointed an instrument at anything resembling a rotation curve. She was born in Philadelphia in 1928. The family moved to Washington when she was 10, and she was the kind of child who watched stars from her bedroom window because nothing else available to her seemed as interesting. She has described lying awake, tracking their movement across the frame of the window, and building a cardboard telescope with her father, who was an electrical engineer and who took the enthusiasm seriously enough to drive her to meetings of amateur astronomers. She earned a degree in astronomy from Vassar College in 1948, one of the few American institutions then willing to train women in the sciences. She had wanted to go to Princeton. Princeton did not admit women to its graduate astronomy program, and would not for another 27 years. She went to Cornell for a master's degree instead, and then to Georgetown University for a doctorate, completed in 1954, working under the physicist George Gamow. The obstacles along the way were not subtle. A science teacher early in her education advised her plainly to stay away from the field. At Cornell, after she submitted a thesis her advisor dismissed as sloppy, that same advisor offered to present her research at a meeting of the American Astronomical Society under his own name, on the grounds that she was pregnant at the time, and would therefore be an inconvenient messenger for her own work. She declined, and went herself. Years later, When she became the first woman formally permitted to observe with the telescopes at Palomar Observatory, she found there was no women's restroom on the site. She dealt with it by locating a bathroom, cutting the shape of a skirt out of paper, and taping it to the door. Her early research was ambitious, and it got her into trouble. Her master's work argued that galaxies might not be distributed randomly through space, but might be rotating together around some common center. It was not well received. Later, working with Kent Ford in the 1970s, she published evidence for what became known as the Rubin-Ford effect, a suggestion that our own region of the universe was moving relative to the general expansion in a way that the standard picture did not predict. That, too, drew heavy criticism, some of it aggressive, and this is the part of her story that gets left out of the short versions. After the Rubin-Ford controversy, she made a deliberate decision. She went looking for a problem that nobody would fight her about, something quiet, technical, uncontroversial, where she could work carefully and be left alone. She chose the rotation curves of spiral galaxies, measuring how fast the material in a galaxy orbits at different distances from its center. It was considered routine, textbook, the sort of thing you do to fill in a table. She had picked, without knowing it, the most consequential observational problem in 20th century astronomy. By the 1960s, she was at the Carnegie Institution's Department of Terrestrial Magnetism in Washington, where she began a long working partnership with an instrument builder named Kent Ford. Ford had made something few other observatories could match: an image tube spectrograph, using an electronic tube to amplify faint light before it reached the photographic plate. It cut exposure times dramatically. Measurements that would have taken many nights could be done in one. It let them reach the outer parts of galaxies where the light thins to almost nothing, and it is not an exaggeration to say that the discovery belonged to the instrument as much as to either of them. They chose the Andromeda galaxy first, the nearest large spiral to our own, big enough on the sky to be measured in detail, close enough that the faint outer regions were within reach. The expectation going in was the same expectation the field had carried since Newton, and the same one Horace Babcock had carried 30 years earlier. Planets close to the Sun move fast. Planets far from the Sun move slowly, because the pull weakens with distance and the orbital speed adjusts. Most of a spiral galaxy's visible mass sits concentrated toward its bright center. Stars far out near the faint edges should therefore orbit more slowly than stars close in, the way Neptune moves more slowly than Mercury. They published their first results on Andromeda in 1970, tracing the rotation out to roughly 110 arc-minutes from the center far past where most previous studies had bothered to look. The curve did not fall. Stars far out at the edge of the visible galaxy were moving at essentially the same speed as stars deep inside it. The line, plotted, went flat and stayed flat, out to the limit of what they could measure. Rubin described what happened next in an interview many years later, and her account is unusually specific about how slow understanding actually is. Months, she said, were taken up simply trying to understand what she was looking at. Then one day she decided she had to understand the complexity in front of her, made sketches on a piece of paper, and in her words suddenly understood it all. If a galaxy carries an unseen halo of mass wrapped around it, extending well past the edge of its visible stars, then as you move outward you keep enclosing more mass. The pull does not weaken the way it should, and the orbital speeds even out. A flat curve is exactly what you would expect to see. Months of not understanding, and then an afternoon with a pencil. She and Ford, with a third collaborator, Norbert Thonard, took that insight and tested it against galaxy after galaxy. They announced their broader findings at a meeting of the American Astronomical Society in 1975, published fuller results in 1978, and published again in 1980 with a sample of more than 20 spirals covering a wide range of sizes and brightnesses. The pattern held nearly everywhere, spiral after spiral, the same flat curve, the same implication. Whatever holds these systems together extends far past the visible disk of stars, and it considerably outweighs the disk. They were not working alone, and Rubin was consistent in saying so. At the same time, in the Netherlands, a graduate student named Albert Bosma was completing a doctoral thesis using radio observations of neutral hydrogen, the same 21 centimeter technique that had been applied to Andromeda in the 1950s, now applied systematically to a whole sample of galaxies and reaching even further out than the optical measurements could. His curves were flat too, at radii well beyond anything Rubin and Ford could see. Optical and radio, two entirely different instruments, measuring two entirely different things. Agreeing, by the early 1980s the field could no longer set the question aside. What had been an isolated, half-believed claim about a few distant clusters was now a property of ordinary, nearby, thoroughly studied galaxies, observed repeatedly and independently, in two separate parts of the electromagnetic spectrum. Rubin herself was careful about the language. She avoided the term dark matter in much of her published work, preferring to describe what she had found as non-luminous matter, and letting the data carry the argument rather than the label. She never claimed sole credit for the insight, crediting Ford's instrument and their shared observing throughout her career, and describing the pursuit as a collective effort rather than a personal triumph. She spent a good deal of her later life doing something else as well, pushing, persistently and by name, for women to be included in observing programs, on committees, and in the membership of institutions that had spent decades excluding them. She died on Christmas Day of 2016, at the age of 88. By then, she had received nearly every honour a working astronomer can receive: election to the National Academy of Sciences, the National Medal of Science, the Gold Medal of the Royal Astronomical Society. The previous woman to receive that award had received it in 1828. Times, she never received the Nobel Prize in Physics, and because the Nobel Committee does not award prizes posthumously, her death did not simply mark the end of a career. It closed, permanently, any possibility that the discovery she is best known for would be recognized at that level. The explanation usually offered, in the years before her death, was that dark matter remained too unconfirmed, still an inference, rather than a directly observed particle. On its own, that sounds reasonable. It becomes harder to sustain when you notice that the 2011 prize in physics was awarded for the discovery of dark energy, which is no more directly observed, no less inferential, and which was confirmed through observations made 2 full decades after the rotation curve work had already established the case for unseen mass. One colleague, reflecting on it afterward, put the matter simply: she had won essentially every scientific award available to her, except the single one that carries the most public weight, and by the end the absence had stopped looking like an oversight. There is a detail about the Andromeda measurement that is easy to skip past and worth slowing down for. What they were actually measuring, out at those enormous distances from the centre, was not starlight from individual stars. It was the light of ionized hydrogen regions, glowing clouds scattered through the outer disk, each one lit from inside by hot young stars. Those clouds emit at very specific wavelengths, which is what makes a velocity measurement possible. You look at where the emission line sits relative to where it should sit, and the shift tells you how fast that patch of the galaxy is moving toward or away from you. So a rotation curve is not one measurement, it is dozens of separate measurements of separate objects at separate distances from the centre, each requiring its own exposure, each with its own uncertainty, assembled afterward into a line. Building one for a single galaxy was a substantial piece of work. Rubin and Ford built them for dozens. And the flatness is more specific than it sounds. It is not that the outer velocities were somewhat higher than predicted. It is that the curve, plotted, was almost perfectly level all the way out, the same speed at 60,000 light-years from the centre as at 20,000 in galaxy after galaxy. Regardless of how the visible light was distributed, that level line is a very particular thing to demand of a mass distribution. It requires the enclosed mass to keep growing in almost exact proportion to the radius, far beyond where the stars run out. Not a bit more mass than expected. A precisely tuned amount in a specific arrangement, extending out into apparently empty space. There is a version of this story that stops here, treating rotation curves and cluster velocities as the whole case, and it would be a comfortable place to leave it for the night. But the two methods have something in common that needs saying plainly. They both measure motion, a velocity, a rotation speed, a spread of galaxies drifting relative to one another. All of it is inference, worked backward from how things move to how much unseen mass must be moving them. Neither Zwicky nor Rubin ever saw the mass. Neither method produces a picture of where the missing matter actually sits, only a number for how much of it there has to be. Which leaves an obvious next question, and it is the question that would take this field somewhere their instruments could not reach. Is there any way to do better than inference from motion? Any way to watch this mass act directly on something other than a spinning galaxy, and ideally, to find out whether it sits in the same place as the visible material or somewhere else entirely? There is. The physics behind it had been written down in 1915, and the man who first suggested using it as a scale for dark matter was, of all people, Fritz Zwicky. Albert Einstein finished the general theory of relativity in 1915, and one of its predictions was that mass does not simply pull on other mass. Mass bends the space around it, and light travelling through bent space bends along with it. A sufficiently massive object sitting between Earth and something further away should act like a lens, distorting, smearing, occasionally doubling the image of whatever lies behind it. The first test came 4 years later. In May of 1919, expeditions led by the British astronomer Arthur Eddington travelled to Brazil and to an island off the west coast of Africa to photograph a total solar eclipse. The idea was to catch the light of stars passing close to the edge of the sun at the one moment when the sun's own glare was blocked, and to see whether those stars appeared shifted from their usual positions. They did. The measurement was crude by later standards, and the error bars were generous, but it was enough. Light bends around mass. Einstein became, more or less overnight, a public figure. Bending starlight around the sun is one thing. Using it as a measuring instrument on galaxies is another. And the person who first proposed doing so was Fritz Zwicky. In that 1937 paper, 2 years before Babcock's rotation curve, and 42 years before anyone actually observed the effect, he argued that clusters of galaxies would be massive enough to lens objects behind them, that such lenses would be found if anyone looked, and the crucial point that measuring the distortion would give the mass of the lens directly, without any assumption about how much light it produced. The first confirmed gravitational lens turned up in 1979, a pair of quasars in the northern sky sitting close together, with spectra so nearly identical that the only sensible explanation was that they were one object, its light split into two paths by a galaxy in the foreground. It became known as the twin quasar. After that, examples accumulated quickly: arcs, rings, multiple images, and the subtler, statistical kind of distortion, where thousands of background galaxies are each stretched very slightly in the same direction, and the pattern only emerges when you measure them all. That statistical kind is what turned lensing into a mass measuring tool, and it is a genuinely different kind of tool from anything Zwicky or Rubin had. Rotation curves and cluster velocities work by inference. You watch how fast something moves, and you calculate backward to the mass required to explain that speed. Lensing does not work that way. It measures the total gravitational effect of everything sitting in front of a distant light source, directly, from the shape of the distortion in the image. It does not care whether the mass glows, it does not care what the mass is made of. If the mass is there, the light bends, and the amount of bending tells you how much. Which meant that by the early 2000s, physicists finally had a way to ask a very specific question. Not how much unseen mass is there, they had a reasonable answer to that already, from 3 directions. The new question was, where is it? Does the invisible mass implied by rotation curves sit in the same place as the visible matter, or somewhere else? In 2006, an answer arrived from an object roughly 3.8 billion light-years away in the southern sky. It has a formal catalogue designation, a string of numbers and letters, but nobody uses it. Everyone calls it the bullet cluster. It is not one galaxy cluster. It is 2, caught in the act of colliding, a collision that began roughly 150 million years before the light we now receive left the scene, between 2 clusters that were moving relative to one another at somewhere in the range of several thousand kilometers per second. It is one of the most energetic events currently visible anywhere in the sky. A research team led by Douglas Clow was granted more than 100 hours of observing time on the Chandra X-ray Observatory to study the aftermath, and combined that data with optical and lensing images from the Hubble Space Telescope, from the Very Large Telescope in Chile, and from the Magellan telescopes. What the X-ray data showed was gas. Ordinary, hot, ionized gas, heated by the collision to temperatures in the range of 160 million degrees. This is the part people find surprising the first time they hear it. In a galaxy cluster, the gas is the dominant form of ordinary matter, not the stars, not the galaxies. The thin, superheated gas filling the space between the galaxies outweighs everything in them by a considerable margin. If you want to know where the ordinary matter of a cluster is, you look at the X-rays, and in the collision, that gas behaved exactly the way two enormous clouds of gas should behave when they run into each other. It collided, it dragged, it produced a shock front, a visible bow wave of compressed material, and it piled up in the middle, an icon 12, between the two clusters, distorted into the elongated shape that gives the object its name. Two smears of glowing gas, slowed and left behind by the impact, sitting between the two clusters that carried them in. Then came the second image, and it was built from something else entirely, using the shapes of thousands of faint background galaxies lying far beyond the cluster. The team reconstructed a map of where the total mass sat, the mass responsible for bending all that light. If dark matter did not exist, and the missing mass problem was really about some flaw in our understanding of gravity, this second map should have matched the first. In that scenario, the gas essentially is the matter. The gravitational pull should be strongest where the gas is thickest. The two maps should sit on top of one another. They did not. The lensing map showed two separate concentrations of mass, offset from the gas entirely, sitting instead right on top of the two clusters' galaxies. The galaxies, unlike the gas, had passed straight through each other during the collision with almost no interaction at all. That sounds implausible until you consider the spacing. Galaxies inside a cluster are separated by distances so vast, relative to their own size, that two clusters can pass completely through one another without a single direct collision between individual galaxies. They are, from the point of view of the collision, mostly gaps. The gas, by contrast, is continuous. It fills the space. It cannot pass through itself. So the collision sorted the cluster into two components. The gas, which interacts, was shocked and slowed and left in the middle. The galaxies, which do not effectively interact, sailed through and kept going. And the bulk of the mass went with the galaxies. That separation is the entire argument. Whatever makes up most of the mass in the bullet cluster does not interact with itself or with ordinary matter the way gas does. It does not collide. It does not shock. It does not slow down when it passes through another cloud of the same material. It moves under gravity and nothing else, indifferent to the enormous, violent event playing out in the ordinary matter around it. The team quantified the significance of the offset at 8 sigma, a statistical statement meaning, roughly, that the chance of the separation being an artifact of noise is somewhere down in the range of 1 in many billions. The press materials at the time described it as direct empirical proof of the existence of dark matter. That is strong language for a press release. It held up under scrutiny for the better part of 2 decades from a field that is not generally inclined to accept press release language without testing it first. For close to 20 years, the bullet cluster held a particular status in this argument. It was not simply another piece of supporting evidence. It was widely regarded as the single hardest case for rival theories to explain away, for the theories that try to account for the missing mass, not by adding an invisible substance, but by changing the rules of gravity itself. The reason it is hard for those theories is worth stating precisely, because it is not a vague difficulty. A modification to gravity changes how strongly mass pulls. It does not change where the mass is. So in a modified gravity picture, the strongest gravitational effect should still be centered on the largest concentration of ordinary matter, whatever the strength of the pull happens to be. In the bullet cluster, the largest concentration of ordinary matter is the gas, sitting in the middle, glowing at 160 million degrees, and the gravitational effect is not centered there. It is centered somewhere else, on either side, in regions with far less ordinary matter in them. You can adjust how strongly gravity pulls. It is much harder to explain why it would pull hardest from a place where most of the visible material is not. It is worth explaining how the second map is actually made, because it sounds like magic, and it is closer to statistics. Behind any cluster of galaxies, there are thousands of much more distant galaxies, faint and small on the sky. Each one has some intrinsic shape. Some are round, some are elongated, and they are oriented every which way, essentially at random. When their light passes through the gravitational field of the cluster on its way here, each image gets stretched very slightly, in a direction determined by where the mass sits. The stretch is tiny. For any individual galaxy, it is completely swamped by that galaxy's own natural shape. You cannot look at one distorted galaxy and learn anything. But the distortion is not random, and the intrinsic shapes are. So if you measure the shapes of many thousands of background galaxies and average them, the random part averages away and the systematic part survives. What emerges is a faint, coherent pattern of alignment across the field galaxies, preferentially stretched into arcs around some central point, and from the strength and geometry of that pattern you can reconstruct where the mass is. This is called weak lensing, and it is one of the more remarkable measurement techniques in physical science. An image of something invisible, assembled from the barely perceptible distortion of thousands of unrelated objects that happen to lie behind it. Closer in, where the field is strongest, the effect stops being subtle. There you get strong lensing, dramatic arcs, and occasionally complete rings, where a background galaxy sits almost exactly behind the center of the cluster, and its light is wrapped all the way around. Those give very precise mass measurements for the inner regions. The two techniques together, strong lensing inside and weak lensing outside, produce the full map. The bullet cluster does one further thing that is easy to miss. It does not only show that the mass is separated from the gas, it puts a numerical limit on how much dark matter can interact with itself. If dark matter particles collided with one another to any significant degree, then during the collision the two dark components would have slowed each other down, at least partially, and lagged behind their galaxies. They did not measurably lag. From the absence of that lag, you can calculate an upper bound on how strongly the particles can interact with themselves, a real quantitative constraint on the properties of a substance nobody has ever isolated. Several proposed models of self-interacting dark matter, invented to solve unrelated problems in the structure of small galaxies, run into that bound. That was where the argument stood, treated by most of the field as close to settled, for a very long time. Textbooks used the image. Public lectures used the image. If you have ever seen a picture of dark matter, you have almost certainly seen that one, the pink smears and the blue clouds, sitting apart. And then, this year, a team pointed a new instrument at it and found that the picture was more complicated than anyone had been able to see. The instrument was the James Webb Space Telescope, and the team was led from the University of Bonn in Germany, specifically from the Helmholtz Institute for Radiation and Nuclear Physics there, with a first author named Dong Zhang. The collaboration was unusually spread out. Bonn, Portsmouth in England, Yonsei in Seoul, Prague, Wuppertal, Nanjing, with visiting researchers from institutes in Zanjan and Tehran. Their analysis was published this year in the journal Physical Review D. What the Webb telescope brought to the bullet cluster was not a new kind of measurement, it was resolution. The original analysis had used the best available data of its time, and the best available data of its time was blurrier than what exists now. When you point a sharper instrument at an object that has been studied for 20 years, you do not usually overturn it. What you usually do is see the places where the earlier picture had been smoothed over. Two things came out of the new data. The first was a much better count of the ordinary matter. Webb can resolve the stellar populations of both clusters far more precisely than earlier instruments, which means a far more accurate estimate of how many stars are actually there. And there was a second thread, which is the interesting one, and it comes from chemistry rather than from counting. The bullet cluster's gas contains a large quantity of heavy elements, iron, oxygen, and others. Those elements are not primordial. The early universe made hydrogen, helium, and traces of lithium, and essentially nothing else. Everything heavier was manufactured inside stars, and specifically, the elements found in that gas in those proportions require very massive stars. Massive stars burn fast and die violently. What they leave behind after the explosion is a neutron star or a black hole, so the presence of those heavy elements is a receipt. It tells you that a large population of massive stars once lived and died in these clusters. and if a large population of massive stars lived and died there, then a large population of stellar remnants must still be there, now neutron stars and black holes scattered through the clusters, invisible to any telescope because they emit essentially no light of their own. They do, however, have mass, and mass bends light. One of the co-authors, Indranil Banik, at the University of Portsmouth, worked through whether the newly counted visible stars, plus the population of remnants implied by the chemistry, could account for the observed lensing on their own. His conclusion was that a substantial part of it could be explained this way, that the remnants of dead massive stars can take on some of the role that has been assigned to dark matter. There was a third finding, and it is the one that made the paper more than an accounting exercise. Looking closely at the sharper data, the team found that the lensing distortion in the background galaxies was not strongest, where the reconstructed mass concentrations had been thought to sit. It was strongest around the two clusters positioned on either side of the main collision regions that contain comparatively little visible mass. If the lensing is supposed to track where the greatest concentration of mass is, and the strongest lensing turns up somewhere with less visible material to explain it, then something in the standard reconstruction needs another look. Their overall conclusion, stated in the paper and repeated by the team afterward, is that the observations are also consistent with an explanation that does not require exotic dark matter particles at all, and that if dark matter is present in the bullet cluster, the amount required is smaller than has been assumed. In the standard picture, once you account properly for the stellar remnants, the dark matter requirement drops by roughly half. Pavel Krupa, one of the Bonn authors, put the finding in blunt terms. The remnants of massive stars take on the role of dark matter to a certain extent. Now, here is what that does and does not mean, and it is worth being precise, because this is exactly the kind of result that gets reported badly. It does not mean dark matter has been disproven. Nothing in this analysis touches the acoustic peaks in the oldest light in the sky. Nothing in it touches the flat rotation curves of nearby spiral galaxies. Nothing in it touches the deuterium abundance from the first 3 minutes. Those measurements do not depend on the bullet cluster in any way. They were made with completely different instruments on completely different objects, and they have not moved. What has moved is narrower and more specific. One particular object held up for 20 years as the cleanest, most direct, most visually obvious proof available. The one image that closed the argument in a public lecture can no longer be treated as the closing argument. It has become contested. The people contesting it are working astrophysicists publishing in a peer-reviewed journal using the best telescope ever built, and their claim is not that dark matter is absent, but that the amount needed is smaller, and the evidence is more ambiguous than the textbook version admits. 10. There is something worth sitting with in that, and it is not really about dark matter. A result does not have to be wrong to be reopened. It only has to be looked at again by something sharper. The 2006 analysis was not sloppy. It used the best data available from 3 separate observatories, cross-checked against one another, and it survived intense scrutiny for 2 decades, specifically because nobody could yet look closely enough to find its limits. Then somebody could. That is not a failure of the earlier work. It is what happens to every measurement in this field eventually. Once the tools improve enough to ask a more precise version of the same question, Zwicky's distance to the Coma cluster was off by a factor of 10, and his conclusion survived. The bullet cluster's mass reconstruction has been revised, and the broader case for dark matter survives. What changes is the confidence attached to any single piece of it. It is also worth noticing what the new explanation actually is, because it has a certain symmetry to it. The proposal is that some of the missing mass is made of dead stars, burnt-out remnants, too dark and too compact to see. That is very close to what Zwicky himself thought dark matter would turn out to be in 1933. Cold, faint, ordinary material. Invisible only because it does not shine. The field spent 90 years moving away from that idea towards something exotic. A part of it is now, tentatively, moving back. Not all the way back. Nobody involved is claiming that stellar remnants can account for the 26% measured in the oldest light in the sky, and the microlensing surveys we will get to shortly put hard limits on how much of a galaxy's halo can be made of compact objects. The claim is local and specific. In this one cluster, the books balance better than expected once you count the corpses of massive stars. So the picture at this point is neither a clean confirmation nor a clean refutation. It is something less comfortable than either. One of the 2 or 3 strongest pieces of physical evidence for dark matter reopened under active re-examination, with the outcome not settled. That is not a flaw in how the story is being told tonight. It is an accurate description of where the physics currently stands, in the middle of 2026. It is worth understanding what a sharper instrument actually buys you here, because resolution sounds like a cosmetic improvement, and it is not. Every lensing mass map is a reconstruction. You measure the shapes of background galaxies, and you solve backward for a distribution of mass that would produce those shapes. That problem does not have one unique answer. Many different mass distributions can produce very similar distortion patterns, and the way you choose between them is by having enough measured galaxies at high enough resolution to constrain the solution tightly. With blurrier data, you can measure fewer background galaxies reliably, and each measured shape carries more uncertainty. The reconstruction comes out smoother than reality, and smoothness hides structure. So the earlier map was not wrong in the sense of being fabricated. It was the smoothest mass distribution consistent with the data available, and the data available was not sharp enough to demand anything more complicated. When a sharper instrument measures the same field, more background galaxies become usable, the shapes become better determined, and the reconstruction is allowed to show detail it previously had no grounds to show. Sometimes the detail confirms what was assumed. Sometimes, as here, it does not sit where anyone expected. This is also not an isolated event. Since it began operating, the Webb telescope has been steadily complicating pictures that were considered stable, finding galaxies at early times that look more massive and more mature than the standard model comfortably predicts, finding supermassive black holes earlier than they should exist, finding small red objects nobody has fully explained. Not one of these has overturned the standard cosmological model. Several of them have made parts of it look less finished than they did 5 years ago. A telescope that resolves better than its predecessors will always do this, and the honest response is neither to declare a revolution nor to wave it away. It is also worth knowing that this is not the only cluster collision ever studied, and that the others do not all tell the same tidy story. Several more have been found since systems given names like the musket ball cluster, caught at a later stage of the same kind of merger, and a handful of others where the gas and the mass appear separated in the expected way. Those are supporting evidence, and they get cited as such. But there is one that has never fitted, and it does not get cited nearly as often. A cluster in the northern sky, catalogued long ago and nicknamed the train wreck for the obvious reason, appears to show something that ought to be impossible in the standard picture. Analyses of its lensing map found a dense concentration of mass sitting in the middle of the collision, in the same place as the hot gas with no corresponding concentration of galaxies. A dark core where the mass stayed behind with the gas instead of sailing through with the galaxies. That is precisely backwards. If dark matter does not interact, it should not have been slowed by the collision. It should have kept going, the way it did in the bullet cluster. Something that stops when it hits another cloud of itself is not behaving the way the whole argument requires. The finding has been contested since it was published. One reanalysis, using different data, reported no dark core at all. A subsequent analysis by another group reported that it was still there. The dispute has not fully resolved, and the honest summary is that a complicated, messy, multi-way collision is very hard to reconstruct. And this one may simply be a system where the assumptions behind the reconstruction break down. That is probably the right answer. It is also worth noticing the asymmetry in how the two objects have been treated. One cluster produced a result that supported the consensus and became the single most reproduced image in the field. Another produced a result that did not, and remains a specialist footnote with a contested literature attached. Nobody did anything improper. Both objects were studied carefully by competent people, and the messy one really is harder to interpret. But if you only ever encountered this subject through the popular version, you would know one of these clusters by sight and would never have heard of the other. What happens next is ordinary and slow. Other groups will reanalyze the same Webb data with different assumptions and different reconstruction methods and report whether they see the same thing. Some will not. There will be an exchange of papers about methodology, of the same shape as the exchange still going on about the distance to a certain faint galaxy, we will come to shortly. Somewhere in the next several years, the field will settle on a view, and it will probably be less dramatic than either the original claim or the pushback, which forces a question back into view that most accounts of this subject treat as long since closed. If even the bullet cluster can be complicated by better data, if the single most reproduced image in the whole argument turns out to have room in it for a different reading, then how seriously should anyone take the alternative? Not the alternative that chips away at one piece of evidence, but the one that removes the need for dark matter altogether by changing the rules of gravity itself, everywhere, from the ground up. There is such an alternative. It was proposed 4 decades ago by a physicist working essentially alone, and it was rejected by 2 journals before it found a publisher. It is not a fringe position, it is not held by cranks, and it has a specific, verified predictive success attached to it that the standard picture does not. His name is Mordechai Milgrom. He was born in Romania, raised in Israel, took his doctorate at the Weizmann Institute of Science, and spent the 1970s working on high-energy astrophysics, X-ray sources, jets, a well-regarded model of a peculiar star system. Then, around 1981, he started thinking about galaxy rotation curves, and he asked a question that almost nobody was asking. Everyone else was asking what the missing mass was made of. He asked whether it was missing at all. The papers were submitted to the Astrophysical Journal in February of 1982, 3 of them, developed partly at the Weizmann Institute and partly during a sabbatical at the Institute for Advanced Study in Princeton. They were published the following year. The first introduced the idea. The second worked through the consequences for individual galaxies. The third dealt with groups and clusters. Getting them into print was not easy. He had already submitted the introductory paper to Nature and been turned down. He submitted it to another journal, Astronomy and Astrophysics Letters, and was turned down again. The referee's objections, by later accounts, were largely matters of principle and taste rather than of data. The proposal offended people's sense of how physics ought to work. The proposal itself is almost embarrassingly simple to state. What if Newton's law of gravity, tested with extraordinary precision inside our own solar system, where accelerations are relatively large, simply stops being accurate at very low accelerations, the kind found at the outer edges of galaxies? Milgrom attached a specific number to the threshold. It works out to about 1/10 of a billionth of a meter per second, every second. To put that in scale, the acceleration holding you against your bed right now is roughly 80 billion times larger. Nothing in ordinary human experience comes anywhere near this threshold. Nothing in the solar system does either, which is exactly the point. Above it, gravity behaves precisely the way Newton said, which is why 3 centuries of planetary predictions still work perfectly. Below it, out in the faint outer reaches of a spiral galaxy, where a star's motion is governed by a pull far gentler than anything near a sun, gravity would behave differently, falling off more slowly than the standard law predicts, in just the right way to hold those outer stars at the speeds actually observed. No invisible halo required, just a small, specific correction applied consistently, everywhere. The idea became known as modified Newtonian dynamics, usually shortened to MOND, and it did something immediately that earned it serious attention rather than dismissal. It predicted something that was already known but unexplained. Long before Milgrom's papers, astronomers had noticed an empirical relationship in spiral galaxies called the Tully-Fisher relation, after the 2 astronomers who published it in the 1970s. It says, roughly, that how bright a spiral galaxy is and how fast it rotates are tightly linked. Brighter galaxies rotate faster, in a relationship far tighter than anyone had a clean theoretical reason to expect. In the dark matter picture, this is a little awkward. The rotation speed is set mainly by the dark halo, and the brightness is set by the stars, and those are supposed to be 2 separate things. Why they should track each other so closely, across galaxies of wildly different sizes and histories, is not obvious. MOND, built from a single acceleration threshold with no reference to Tully-Fisher at all, reproduces the relation almost exactly, as a direct mathematical consequence of the theory, not as something added afterward to fit the data, as an output. That is not a small thing in physics. A theory that predicts an already known but previously unexplained pattern, without having been constructed to do so, earns a kind of credibility that a theory built specifically to explain the thing it is trying to explain does not. The refined modern version, using the total mass of ordinary matter rather than the light, is called the baryonic Tully-Fisher relation, and it is one of the tightest empirical relationships in extragalactic astronomy. Mond predicted its form before it was measured to that precision. There is a broader version of the same success, and it is the strongest single argument the theory has. Take a large sample of galaxies. For each one, at each radius, calculate the acceleration you would predict from the visible matter alone, and compare it to the acceleration actually observed. Plot one against the other. What you get is not a scatter. It is a tight, single curve followed by galaxies of every type. Bright spirals, faint dwarfs, gas-rich, gas-poor. The observed acceleration is determined, to a remarkable degree, by the visible matter alone. This is called the radial acceleration relation, and it is exactly what Mond says should happen. In the dark matter picture, it is not forbidden, but it does require the dark halo and the visible disk to have arranged themselves into an unusually cooperative relationship in galaxy after galaxy, which is something that has to be explained rather than predicted. Other physicists took the basic idea and tried to build it into a fuller theory. Milgrom's original proposal was not, strictly speaking, a theory of gravity at all. It was a formula, a modification to the relationship between force and acceleration, written down in ordinary non-relativistic physics, with no deeper structure underneath it. That is a real limitation. And it was recognized immediately. In 1984, Milgrom worked with the physicist Jacob Bekenstein at the Hebrew University of Jerusalem to embed the idea in a proper field theory, one that conserves energy and momentum properly. Then, in the mid-2000s, Bekenstein went further and produced a relativistic version, a theory called tensor vector scalar gravity. The reason such a thing was needed is worth understanding, because it explains why the bullet cluster matters so much to this argument. Gravitational lensing is a relativistic phenomenon. It falls out of general relativity, not out of Newton. So a modified Newtonian formula, on its own, says nothing whatsoever about how light bends around a cluster. If you want a modified gravity theory that can also handle lensing and cosmology, you need it built on the same relativistic foundation Einstein used, not bolted onto Newton. The tensor vector scalar theory was an attempt to supply exactly that foundation. Now, the honest accounting, in both directions, because this subject attracts more heat than it deserves in either. In its favour, the phenomenological success is real and it is broad. The same framework works with genuine accuracy across an enormous range of scales, from small dwarf spheroidal galaxies to entire galaxy superclusters, using one universal constant rather than fitting a separate halo to each object. Researchers who have spent careers studying both approaches have written plainly that a great deal of the observational evidence usually cited in favour of dark matter can be interpreted equally well as evidence for modified gravity. That is not a claim smuggled in by unqualified outsiders. It comes from working astrophysicists, publishing in peer-reviewed journals, taking the comparison seriously on its own terms. And the theory has been tested, and could have failed many times over 4 decades, and has not simply collapsed. Against it, and this is equally real, it has never fully solved the cluster problem. Galaxy clusters have been a difficulty for Mond from the beginning. Apply the modification to a cluster and it improves the mass discrepancy but does not close it. You are typically still left needing a factor of 2 or so of additional unseen mass, which is an awkward position for a theory whose entire appeal is that it removes the need for unseen mass. And the bullet cluster is the sharpest form of that difficulty, for the reason given earlier. A change in the strength of gravity does not relocate where gravity pulls from. Explaining why the effective pull sits apart from the bulk of the visible gas remains genuinely unresolved for modified gravity, and the strongest advocates of the theory have not closed it, even as they continue to refine their models. The Bonn analysis discussed a moment ago is in fact an attempt to close exactly that gap, which is why it came from a group that includes people working on modified gravity. There is something almost circular in that, and it is worth naming. The same object works against both sides of this argument at once. It complicates the cleanest piece of evidence for dark matter in one direction, and it remains the hardest single case for modified gravity to explain away in the other. Both camps have spent 20 years pointing at the bullet cluster and drawing opposite conclusions from it, and this year both camps got slightly less comfortable. There is one more difficulty for modified gravity that deserves mentioning, because it is the one most physicists would name first if asked: the acoustic peaks. The pattern in the oldest light in the sky is produced by ordinary matter oscillating in a fluid, while something that does not feel radiation pressure quietly deepens the gravitational wells around it. That second component is doing specific, structural work in the calculation. It is not obvious how to reproduce the observed pattern of peaks without something that behaves like matter and does not interact with light. Relativistic versions of modified gravity have attempted it. None of them has produced a fit to the sky as clean as the standard model does, and this, more than anything about galaxies, is why the majority of the field holds the position it holds. So the fair summary, 40-some years after those 3 papers were finally accepted, is this: modified Newtonian dynamics is a serious, still active scientific position held by credentialed researchers who have real predictive successes in their framework, and it has never been dismissed by rigorous testing the way a genuinely fringe claim would be. It is also not the majority position, and there are specific, articulable reasons for that which have nothing to do with prejudice. There is a version of the objection to modified gravity that is not about evidence at all, and it deserves an airing because it is the one most often made informally. The complaint is aesthetic, that adding a new particle to the universe is a modest, conservative move, since physics has added many particles before, and they keep turning out to exist, whereas altering the law of gravity is an extravagant one. The counter-complaint is that this has the accounting backwards. The standard picture requires a particle that has never been detected, does not appear in the standard model of particle physics, has resisted 40 years of dedicated searching, and whose properties are inferred entirely from the phenomenon it was introduced to explain. Whether that counts as conservative depends on where you were standing when you started. Neither of these is an argument. They are intuitions about what kind of surprise the universe is more likely to deliver, and the history of the subject does not obviously favour either one. Newton's law was itself modified once already, by Einstein, and the modification turned out to matter enormously in exactly the regime nobody had been able to test. What can be said cleanly is this: modified gravity does better than the standard picture at the scale of individual galaxies, where its predictions are sharp, testable, and repeatedly confirmed. The standard picture does better at the scale of clusters and at the scale of the whole universe, where modified gravity has never produced a fully satisfactory account. Those are not the same kind of success, and there is no agreed exchange rate between them. It is also possible, and a small number of researchers argue this seriously, that both are partly right, that there is some dark matter, and that gravity also behaves differently at low accelerations. That position has the disadvantage of being harder to test and the advantage of not requiring either camp to be simply wrong. That tension, a live dispute between two serious explanations, neither one closing the case, is where this part of the story has to sit tonight, without resolving into a verdict. But there is a separate question underneath this whole debate, and it does not get resolved by picking a side. It is the kind of question that only becomes visible once you notice that the two explanations, whatever else divides them, make one prediction that differs sharply, and somewhere in the sky, about 65 million light-years away, there may be an object that tests it. Here is the prediction where the two explanations come apart. If dark matter is a substance actual particles, distributed unevenly, capable of clumping thickly around some galaxies and thinly around others, then, somewhere in the sky, there ought to exist a galaxy where the clumping did not happen. A galaxy built almost entirely of ordinary matter, with little or no dark halo around it. In the standard picture, that would be unusual and would need explaining, but it is permitted. The amount of dark matter around any one galaxy is a matter of history and circumstance, and history is full of accidents. Modified gravity does not have that freedom. Its central claim is that gravity itself behaves differently below a certain acceleration, everywhere, without exception. There is no dial to turn per galaxy. If a galaxy is found whose outer material moves exactly as ordinary Newtonian physics predicts, from its visible mass alone, no boost, no excess, nothing extra, That is a serious problem for a theory that says the boost is a property of space rather than a property of the galaxy. So, find a galaxy without dark matter, and you have said something important. Not a final verdict, but a real constraint, pointing in one direction. In 2018, a team led by the astronomer Pieter van Dokkum at Yale University announced they had found one. The instrument that found it is worth describing, because it is unlike anything else in this story. Most of the telescopes here have been large mirrors on mountains or in orbit, built to collect as much light as possible from very small patches of sky. This one is a rack of commercial telephoto lenses, the kind sold to sports photographers, bolted together and pointed at the sky in parallel. It is called the Dragonfly Telephoto Array, and it exists because the specialized coatings on those lenses scatter light unusually well, which makes them extraordinarily good at picking up faint, extended, low surface brightness structures that conventional telescopes wash out. It was built to find things that are large and dim rather than small and bright. The galaxies it finds carry the initials of the array in their names, which is how an object came to be catalogued as a member of the group around the elliptical galaxy, NGC 1052, designated Dragonfly 2. It sits roughly 65 million light-years away, a companion to that much larger elliptical. It had in fact been catalogued decades earlier, in the 1970s, but nobody had looked at it closely enough to notice anything unusual. What the fresh look found was strange from the first glance. The galaxy is roughly the physical size of the Milky Way, but it contains something like 200 times fewer stars. A vast, diffuse, almost transparent structure. You can see background galaxies through it in the Hubble images. It belongs to a class of object called ultra-diffuse galaxies, which had only been recognized as a distinct population a few years earlier, when a survey of the Coma cluster turned up dozens of them at once. Astronomers had essentially been looking past them. The team measured its mass two separate ways, using the same two-track method Zwicky had used on the Coma cluster 85 years earlier, now on a vastly smaller and more local scale. Once from the visible stars, once from motion, the stellar mass came out to roughly 200 million times the mass of the Sun. For the motion, they used 10 unusually bright globular clusters orbiting within the galaxy, measuring their velocities spectroscopically at the Keck telescopes in Hawaii. The spread of those velocities, the velocity dispersion, came out remarkably low, under 10 kilometers per second, by their analysis, and their best estimate was considerably lower than that. For comparison, the stars in the outer Milky Way are moving at more than 200 kilometers per second. A low dispersion means a weak gravitational field means very little mass, and the dynamical mass they calculated came out barely larger than the stellar mass alone. For virtually every other galaxy ever measured this way, the dynamical mass dwarfs the stellar mass sometimes by a factor of tens, sometimes hundreds, because of exactly the invisible halo Rubin and Ford had documented. Here, the halo appeared to be missing almost entirely. The galaxy seemed to be made of what you could see. The globular clusters themselves added a second oddity. They were unusually large and unusually luminous, rivaling in size and brightness Omega Centauri, the largest and brightest globular cluster orbiting our own galaxy. Not one of them, several. A faint, ghostly, nearly transparent galaxy, apparently missing its dark matter, wearing a small crown of globular clusters bright enough to be remarkable in their own right. Nothing about the object matched the standard picture cleanly, in either direction. The challenge arrived almost immediately, and it was about distance. This is the vulnerable joint in the whole argument, so it is worth making the logic explicit. To convert what you observe into a mass, you need to know how far away the object is. A galaxy that is nearer than assumed is intrinsically fainter than assumed, which means fewer stars, which means less stellar mass. And a lower stellar mass, with the same measured motion, means you need more unseen mass to explain the dynamics, not less. So the entire claim hangs on the distance. Van Dokkum's team had measured roughly 19 to 20 megaparsecs, using a technique based on how much the brightness of the galaxy's light fluctuates from pixel to pixel, a method that works because a nearer galaxy resolves into individual stars more, producing grainier variation. An independent group using the same technique confirmed it, but a separate team, led by Ignacio Trujillo, argued that the calibration of that technique was not valid for a galaxy of this particular color, applied 5 different distance methods of their own, and got a consistent answer closer to 13 megaparsecs. At that distance, the lack of dark matter dissolves. The galaxy becomes ordinary, with a perfectly normal halo hiding in plain sight. One published response to the original claim argued in its own title that the finding was untenable. That is a real scientific fight, conducted in the literature, about a number. Van Dokkum's team held their position, and the next year, in 2019, reported something that made the situation stranger rather than clearer. A second galaxy in the same group, with nearly identical properties. Same size, same surface brightness, same low dispersion, its own population of unusually luminous globular clusters designated Dragonfly 4. He described finding the second one as just as exciting as the first. That mattered, because a single anomalous object can plausibly be written off as a measurement problem, or a one-off. 2 nearly identical objects in the same small patch of sky is a much harder thing to dismiss. Continued observation of the region turned up something stranger still. The 2 galaxies are not isolated oddities. They sit within a tight, statistically significant linear alignment of roughly a dozen faint galaxies, strung out along the same narrow trail across that patch of sky. Nobody has a settled explanation for why that alignment exists. One proposal is that the whole chain was produced by a single ancient collision between gas-rich galaxies, with the debris condensing into a line of new, dark matter-poor objects which, if true, would be a rather elegant answer, since galaxies formed from stripped gas would not be expected to carry halos. Where does it stand now? Somewhat better for Van Dokkum than it did in 2019, and still not closed. Later measurements using a different and generally more reliable distance indicator, the brightness of the brightest red giant stars in the galaxy, which has a known intrinsic value, have tended to support the larger distance. Follow-up spectroscopy from other groups, using different instruments, has confirmed the low velocity dispersion, both for the globular clusters and for the diffuse starlight of the galaxy itself, and found 16 confirmed globular clusters rather than 10. But the distance has not been settled to the satisfaction of every group involved, and papers arguing the point are still appearing. It is an unusually honest thing to leave hanging in the sky. 2 galaxies, possibly more, which may represent the first confirmed exceptions to a pattern that otherwise holds everywhere, or which may be the product of a distance measurement. Nobody has yet pinned down well enough to trust completely. And for modified gravity specifically, these objects are awkward in a subtle way that is worth naming, because the theory does have a possible escape. In modified gravity, unlike in Newtonian physics, the internal dynamics of a small system can be affected by the external gravitational field it is sitting in. A dwarf galaxy sitting close to a large elliptical is inside a substantial external field, and that field can suppress the modification, making the dwarf behave more Newtonian than it otherwise would. Whether that effect is large enough to account for these 2 objects is exactly what the relevant papers argue about. It is not a free pass, and it is not obviously wrong either. So the object that was supposed to discriminate cleanly between the 2 pictures has not discriminated cleanly. That is a recurring shape in this story. Ultra-diffuse galaxies are worth a moment on their own, because the whole class is a reminder of how much of the sky has simply been missed. They are, by definition, as large as ordinary bright galaxies but hundreds of times fainter, which means that spread across the sky they produce so little light per unit area that conventional surveys record them as noise and discard them. They were not recognized as a population until surveys specifically designed for low surface brightness went looking. Then dozens turned up in a single cluster, and then hundreds, and it became clear that a substantial fraction of the galaxies in the universe are objects nobody had been able to see. Some of them appear to have enormous dark halos for their small stellar content. Some, apparently, have almost none, which is itself informative. If the class were uniform, it would suggest a single formation mechanism. The fact that it is not suggests several, and one of the open questions in galaxy formation right now is what set of histories produces objects this diffuse. End quote. There is one further piece of evidence about these 2 particular galaxies that does not depend on the distance argument at all, and it is worth mentioning because it points the other way from the skeptics. Deep imaging of both objects shows that their outer isophotes, the contours of constant brightness at the faint edges, are visibly distorted, stretched into the kind of shape a galaxy takes when it is being pulled at by the tides of a larger neighbour. A galaxy wrapped in a massive dark halo is protected from that. The halo holds it together. A galaxy without one is far more vulnerable and should show exactly this kind of distortion. Both of them do. That is not proof. Tidal distortion has other possible causes, and the measurement is difficult, but it is an independent property, measured a different way, that lines up with the dark matter poor interpretation rather than against it, which leaves the approach nobody has tried yet tonight. Every method so far, Zwicky's cluster velocities, Rubin's rotation curves, the bent light of the bullet cluster, the ripples in the oldest light, the strange dispersion of a ghost galaxy as a form of watching something far away and reasoning backward. None of them touches the substance. If dark matter is really a substance made of particles, then it is passing through this room right now and through the rock beneath it, and it should be possible, in principle, to build something that notices. People have been trying to build that thing for 40 years. The honest place to start is with what those 40 years have produced, which is nothing. Not nothing in the sense of failure, nothing in the sense of a very specific, very expensive, very carefully engineered absence repeated again and again, each time with better instruments than the last, each time narrowing the space where the answer could still be hiding. Two candidates have carried most of the effort, and they come from opposite ends of physics. The first is the weakly interacting massive particle, universally shortened to WIMP. The appeal of it has almost nothing to do with astronomy. If a particle exists with roughly the mass and interaction strength that the weak nuclear force would suggest somewhere in the range of 100 times the mass of a proton, interacting about as feebly as a neutrino does, then you can calculate how much of it would be left over from the early universe. In the first fraction of a second, such particles would be constantly created and destroyed in equilibrium with everything else. As the universe expanded and cooled, the destruction would stop keeping pace, and a certain population would be left stranded, frozen out, unable to find partners to annihilate with. Run that calculation with the weak force numbers and the leftover amount comes out remarkably close to the observed density of dark matter. Nobody put it there. It falls out of the arithmetic. Physicists call this the WIMP miracle, and for roughly 30 years it made the particle feel less like a guess and more like an inevitability. It also connected neatly to a separate theoretical framework, supersymmetry, which predicted exactly such a particle for entirely independent reasons, and which was widely expected to show up at the Large Hadron Collider. The second candidate has stranger origins. The axion was not invented to explain dark matter at all. In 1977, two physicists, Roberto Peccei and Helen Quinn, were working on a puzzle in the strong nuclear force. The mathematics of that force permits a certain kind of asymmetry, a violation of what is called charge parity symmetry, and there is no reason within the theory why that violation should be small. Measurement says it is not merely small, but essentially zero to a precision of about 10 decimal places. A number that could be anything is instead, apparently, nothing. Peccei and Quinn proposed a mechanism that would drive it to zero naturally. Shortly afterward, Steven Weinberg and Frank Wilczek independently realized that the mechanism implied a new particle. Wilczek named it after a brand of laundry detergent, on the grounds that it cleaned up a problem. Only later did anyone notice that if axions exist in the right abundance, they would behave exactly like cold dark matter, extremely light individually, potentially trillions of times lighter than an electron, but produced in such staggering numbers and moving so slowly that their combined mass could account for the whole of the missing matter. A particle invented to fix an unrelated problem in nuclear physics turns out to be a viable answer to the largest unsolved problem in cosmology. That kind of coincidence is either meaningful or it is not, and there is currently no way to tell. The search for weakly interacting massive particles has meant, overwhelmingly, going underground. The reason is background noise. At the surface, you are being struck constantly by cosmic rays and by radiation from the rock and the concrete and the air. Any of it can mimic the signal you are looking for, so you put a mile of rock over your head, which absorbs essentially all of the cosmic rays, and then you build the detector itself out of the least radioactive materials you can find, and then you surround it with layers of shielding, and then you wait. The most sensitive such instrument built so far is called Zeppelin. It sits nearly a mile underground at the Sanford Underground Research Facility in South Dakota, in the workings of what was once the Homestake Gold Mine, the same mine where, decades earlier, a chemist named Raymond Davis had run the experiment that first detected neutrinos from the Sun, and in doing so opened a different long-running puzzle in physics. There is a certain continuity to the place. The mine closed, the physics stayed. The detector holds 10 tons of ultra-pure liquid xenon, chilled to well below the freezing point of water, with a central region of about 5.5 tons used for the actual search. Xenon is chosen because it is dense, because it is chemically inert, and because it produces both a flash of light and a small cloud of electrons when something strikes one of its nuclei, two independent signals from the same event, which lets you distinguish a nuclear recoil from the far more common electronic background. The whole assembly sits inside a titanium vessel, inside a tank of ultra-pure water, monitored continuously by hundreds of light sensors. It is operated by an international collaboration of roughly 250 scientists and engineers across 36 institutions. Its most recent published results draw on 417 live days of data, collected between March of 2023 and April of 2025, the largest dataset ever assembled in a dark matter search. The collaboration extended its reach downward, looking for the first time at particles as light as roughly 3 times the mass of a proton. They found nothing, no sign of the particle anywhere in that range. The run did produce one genuine result, and it is a strange one. Buried in the same data, the detector picked up its first confirmed signals from neutrinos streaming out of the core of the Sun, specifically from boron-8, one of the rarer branches of solar fusion detected through an extremely subtle process in which a neutrino scatters off an entire nucleus at once, rather than off any individual particle inside it. The detection reached 4.5 sigma, the strongest evidence yet for that process in xenon. That sounds like an unrelated bonus, and it is not. It is the beginning of the end of the technique. Neutrinos, unlike dark matter, definitely exist, definitely stream through these detectors in enormous numbers and produce signals almost indistinguishable from the ones a dark matter particle would produce. As detectors get more sensitive, they will eventually start seeing neutrinos constantly, a permanent, irreducible background that cannot be shielded against, because the whole planet does not shield against neutrinos either. Physicists call this the neutrino fog. It is not an absolute wall, but it is a point past which every further improvement buys much less than it used to. Zeppelin has just taken the first clear look at it. One science writer, summarizing an earlier round of these results, put the broader situation plainly. The 4-decade search for the weakly interacting massive particle appears to be entering its final chapters. Not because the particle has been ruled out, a null result narrows the range of possible masses and interaction strengths without eliminating the idea, but because the space left for it to hide in keeps shrinking, generation after generation, across increasingly sensitive and increasingly expensive experiments, all reporting the same thing. It has not helped that the Large Hadron Collider has now run for well over a decade, and has found no trace of supersymmetry either. The theoretical scaffolding that made the WIMP feel inevitable has not collapsed, but it has become noticeably quieter. The axion search looks nothing like this, because an axion would not strike a nucleus. It would, under precisely the right conditions, convert into a photon. The trick for detecting that was worked out by the physicist Pierre Zwicky in 1983. Put a resonant cavity inside a very strong magnetic field. In such a field, an axion of the right mass can convert into a microwave photon, and if the cavity happens to be tuned to the corresponding frequency, that photon will resonate and become, just barely, detectable. The catch is that nobody knows the mass, and the cavity only listens to one narrow frequency at a time. So you tune, you listen, you hear nothing, you tune again. It is a radio search across a band whose width is unknown and whose station may not exist. The leading instrument doing this is the Axion Dark Matter experiment at the University of Washington. It does not need to be underground, because the background problem is completely different. What it needs instead is cold and quiet. The cavity is a copper-plated cylinder of about 136 litres, sitting inside a superconducting magnet, producing a field of 7.6 Tesla, something like 150,000 times the strength of the Earth's magnetic field. The whole apparatus is cooled by a dilution refrigerator to a fraction of a degree above absolute zero, because thermal noise in the receiver would otherwise drown the signal. The amplifiers are quantum-limited devices operating at the theoretical minimum noise permitted by physics. The project has been running in various forms since the 1980s. In 2018, after 3 decades of refinement, it finally reached the sensitivity required to detect an axion at one of the 2 benchmark theoretical couplings in a narrow band of possible masses. That was a genuine milestone. It was the first time the experiment could have found the particle if the particle were there at that mass. It was not there. The team adjusted the cavity, moved to the next slice, and kept going. They have been working their way across the band ever since, and the amount of unexplored territory remaining is enormous. There is a shift worth naming in how the field talks about these 2 candidates now compared to 20 years ago. One theorist, reflecting on the accumulating null results, described it as a straight substitution. The decline of the WIMP has been matched, almost exactly, by the rise of the axion. Not because axions have been detected, because decades of increasingly expensive searches for the other thing kept coming back empty, and attention and funding went looking for somewhere else to be. Before either of these existed as serious proposals, an earlier generation tried something much simpler in concept. What if the missing mass was not exotic at all, but ordinary matter in a form too dark to see? Dead stars, black holes, brown dwarfs that never ignited, unlit planets, drifting through the space between the visible stars. Objects like these got a name: massive compact halo objects, or MACOs, which was a joke at the expense of the other acronym. The way to find them is elegant. If such an object drifts directly between Earth and a distant background star, its gravity acts briefly as a lens, focusing that star's light and making it appear to brighten and then fade over days or weeks in a very distinctive, symmetric, color-independent pattern. You cannot see the object. You see the star flicker. 2 major surveys set out in the 1990s to look. The MACO project monitored nearly 12 million stars in the large and small Magellanic Clouds, the 2 satellite galaxies of the Milky Way, watching for exactly that signature. Across years of continuous observation, they found somewhere between 13 and 17 candidate events. A separate European survey, the second generation of a project called EROS, monitored 7 million bright stars over roughly 6.5 years and found a single convincing candidate. Those are small numbers, and small numbers are the result. Combined, they could account for only a modest fraction of the dark matter believed to surround our galaxy. The surveys placed an upper limit somewhere under 10% of the halo. Such objects exist. They found a handful. There are nowhere near enough of them. That conclusion has been revisited recently, because the discovery of black hole mergers by gravitational wave detectors revived interest in the idea that primordial black holes holes formed in the first instance of the universe rather than from collapsing stars could make up some fraction of the missing mass. It remains a live minority proposal, but the same microlensing constraints apply, and across most of the plausible mass range, the surveys have already closed the door. So the picture, assembled across roughly a century of work, 4 distinct approaches, and a great many careers spent, comes down to this. There is a third strategy, less discussed than the other 2, which is to make the particle rather than wait for it. If dark matter interacts with ordinary matter at all, then in principle, a sufficiently energetic collision between ordinary particles could produce some. You would never see it, it would leave the detector without interacting, but you would see its absence. Momentum has to balance. If you collide 2 beams head-on, and the debris that comes out is measurably lopsided, then something invisible carried the difference away. Physicists call this a missing energy signature, and it is one of the things the Large Hadron Collider has been looking for since it started running. It has not found one. That is not a small result. The collider searches, the underground detectors, and the searches for the products of dark matter annihilating in space are 3 completely different ways of probing the same hypothetical interaction, and they constrain overlapping regions of the possibilities. All 3 have come back empty across a very wide range of masses and couplings. The region where a weakly interacting massive particle could still be hiding is now a fraction of what it was when the search began. There is a fourth approach worth naming, which does not look for the particle at all. It looks at the shapes of things. If dark matter is genuinely cold and collisionless, simulations predict that galaxies should be surrounded by large numbers of small satellite clumps, and that the density of a halo should rise steeply toward the center. Observations have historically found fewer satellites than predicted, and shallower central densities in small galaxies. These are real, long-standing tensions with names: the missing satellites problem, the Caucus problem, and they have been used for years as arguments that something is wrong with the cold dark matter picture. They have also been steadily shrinking, which is the honest thing to report. Deeper surveys have found many more faint satellite galaxies than were known 20 years ago. Simulations that include the messy physics of exploding stars, rather than gravity alone, produce shallower central densities without changing anything about the dark matter. Neither problem has fully dissolved, and neither now carries the weight it did. Ordinary compact objects have been searched for directly by watching millions of stars for years, and mostly ruled out. Weakly interacting massive particles have been searched for directly, with steadily improving instruments, for more than 40 years, and have not been found, and the technique is now approaching a background limit it cannot shield against. Axions have been searched for directly, with an entirely different kind of instrument, for nearly as long, across a small fraction of their possible mass range, and have not been found either. And every method that works by watching how mass moves Zwicky's clusters, Rubin's rotation curves, Bosma's radio measurements, the bent light of gravitational lensing, the acoustic ripples in the oldest light in the sky, the chemistry of the first 3 minutes agrees, independently and repeatedly, that the mass is there, in the amount described at the very start of tonight. That is not a contradiction. It is simply where the physics sits, a phenomenon confirmed with extraordinary precision by one entire class of tools, and completely unidentified by every attempt so far with the other. It is late now, and this is close to where tonight's story ends. You are still lying in the same room you started in. Nothing about the room has changed. The particles are still passing through it, exactly as they were at the beginning, through the ceiling, through your chest, through the mattress and the floor and the foundation and the rock beneath the foundation, out through the far side of the planet and away into the dark, without slowing, without leaving a mark, without registering that any of it was there. Somewhere between 10 and 100,000 times this year, one of them will happen to strike the nucleus of one of your own atoms. You will never know when. There is no sensation attached to it. There will never be any evidence that it happened to you specifically. On this night, in this room, everything of it, inside every human being currently alive, still comes to less than a single nanogram. And all of it together, across the whole of the universe, still outweighs every star, every planet, every atom of every visible thing ever counted or catalogued or named by roughly 5 to 1. We know this the way you now know it, through a Dutch astronomer counting the vertical motion of nearby stars in 1932 and finding the numbers would not close, through a difficult, isolated man who ran the arithmetic on 7 galaxies in a cluster in 1933 and spent the next 40 years being right and being ignored, through a young astronomer at Lick Observatory in 1939 who measured the rotation of Andromeda, found exactly the wrong answer, and reasonably decided it was dust, through a flat line that 2 people found in that same galaxy 31 years later, sketched out on a piece of paper one afternoon after months of not understanding what they were looking at, through the bent light of 2 clusters caught mid-collision, 3.8 billion years away, a finding now itself being looked at again, more closely than before, by an instrument that did not exist when the finding was made, through the oldest light in the sky, patterned with ripples laid down before a single star had formed, through a faint, nearly transparent galaxy that may or may not have a halo, sitting in an unexplained line alongside a dozen others like it, and through 4 decades of expensive, careful, well-designed instruments built by thousands of people, returning the same patient answer again and again: not here, not yet, keep looking. Vera Rubin did not live to see any of the recent chapters, not the re-examination of the bullet cluster, not the ghost galaxies in the dragonfly field, Not the 10 tons of liquid xenon sitting a mile underground in South Dakota, waiting in the workings of a closed gold mine. She died having shown the field more clearly than anyone before her exactly where to look. The prize that recognizes discoveries of that scale was never given to her while she was alive to receive it, and once she was gone, it became a thing that could not happen at all. What she left behind was not a name attached to an award. It was a flat line on a graph, and a room full of physicists who could no longer pretend the line was not there. There is one more thing, and it happened last month. On a mountain in Chile called Cerro Pachon, an observatory has just begun a survey. It will run for the next 10 years. It carries an 8.4-meter mirror and the largest digital camera ever built, 3.2 billion pixels, roughly the size of a small car. Every 3 nights it photographs the entire southern sky. Over a decade, it will observe each object. It can see something like 800 separate times, building not a picture of the universe, but a time-lapse of it, and it will produce more data than every other observatory in history combined. It was designed, among a small number of stated purposes, to map the distribution of dark matter across a large fraction of the sky using gravitational lensing. The technique Zwicky proposed in 1937 applied to more galaxies than have ever been measured at once. In 2019, the United States Congress voted to name it after her. It is the Vera Rubin Observatory, and it began its survey in June of this year. She has been dead for 9.5 years. The instrument, now doing the most careful work anyone has ever done on the problem she opened, carries her name on the side of the building, and the first 10 years of its data are just beginning to arrive. There is one more number worth placing before the end, because it puts the whole century in proportion. Every direct detection experiment ever built, added together, all the xenon, all the germanium, all the sodium iodide, all the argon, every ton of carefully purified material ever lowered into a mine, for this purpose amounts to a few tens of tons of matter, watched for a few decades. Against that, the thing being searched for is spread across a volume in which our entire galaxy is a speck, and the amount of it that has passed through all those detectors combined, over all those years, would not register on any scale. We are trying to catch a substance by holding out a very small, very quiet, very cold net in the dark, and waiting for something that almost never touches anything to touch this. It has not worked yet. There is no particular reason to think it cannot. 85%. That is the number this whole night has circled, from the first sentence to this one. Not 85% of something distant or abstract, or confined to a textbook. 85% of the matter making up everything, including the room you are lying in, moving through you right now. More of it than every star combined. It asks nothing of you. It does not announce itself. It has never once, in the whole of recorded history, revealed what it actually is. We know where it is. We do not know what it is.